All right, so here's our first application of this damped oscillation. So we've got a spring with a weight hanging from the ceiling is released to bob up and down. The function is given below where d is the distance in inches of a weight from the point at which it's attached to the ceiling. So we've got our ceiling here. We've got a spring attached to it. We've got some sort of weight. Now, the function d gives the distance that the weight is from the ceiling. So it's always going to be positive, right? That's one thing that we should point out. How far from the ceiling will the spring be when it stops? What is its period? By period, I mean its oscillatory period, because we know that the amplitude is going to change. So here's the function. D of t equals 3e to the negative 0.8t cosine of 6 pi t plus 4. So let's look at that first part of that function, 3e to the negative 0.8t. Okay. That is exponential decay, and it looks like this. So this is what's going to be happening to the amplitude. And if I were to copy this and then make it negative, we're going to bound the motion of our weight on our spring between those two curves. So then what's going to happen when we multiply that by the cosine of 6 pi t plus 4? Well, we know what the function cosine looks like. We've got a 6 pi there, and let's use that to address this period concept already. So we've got b equals 6 pi, so our period is going to be 2 pi over 6 pi, so our period is going to be 1/3. Did I give units for time here? I think this is just seconds. I don't think I actually put that in there. Okay. So the period is 1/3 of a second. Every third of a second, it's going to be back to where it was before. So I guess I don't know if that's fast or slow, but on our graph, that's going to be pretty frequent, isn't it? So that is our period, 1/3 of a second. Where will it be when it stops? Okay. Well, take a look at this function. We know when we multiply our exponential decay function times the cosine of 6 pi over t, it's bounding it between those two curves, right? Okay. But now we have that plus 4, and what do we know a plus 4 is going to do to a cosine function? We know it's going to change the midline and slide it up 4. So actually, if we wanted to graph the bounds on here, we actually have to slide those up 4 as well. Okay, so it's going to come to a rest 4 inches from the ceiling. Oops. So we can notice that it's going to start at a distance of, I'm having a hard time getting in there. How far is it going to start from the ceiling? Trying to grab that y intercept. It's going to start at a distance of a hair over 7. And that shouldn't surprise us very much. We know that the cosine of 0 is going to be 1. When we put 0 into this, okay, e to the negative 0.8 times 0, e to the 0 is 1. This is 3. So this ends up being 3 plus 4, which is 7. Now, I'm not exact. There we go. I was going to say, I'm not exactly sure why it's not working out to exactly 7. There it is. There's our point, 0, 7. It starts at 7 units away from the ceiling. Then it gets closer to the ceiling. Then it comes back up right there. And look at that. Where does that happen? It happens at 1/3 of a second. It's taken 1/3 of a second for its oscillatory period to get back where it started from. All right, so it will come to a rest 4 inches from the ceiling. And that's again because that's where the midline was. All right, so this is one where I gave you the function and we were able to get some information from it. we need to reverse that process, don't we? Okay. So here's what we have here. A spring measuring 10 inches in natural length. Natural length is just, it hasn't been stretched or compressed. If it's just laying there, it's at its natural length. Okay, is compressed 5 inches and released. It oscillates once every 3 seconds. Okay, that's a period, isn't it? Its amplitude decreases by 30% every second. Finding the equation that models the position of the spring T seconds after it has been released. Okay. So we've got our sealing again. We've got our spring. And we've got this weight hanging here. All right, so the natural length before it's been stretched or compressed is going to be 10 inches. It is then going to be compressed by 5 inches and then released. It oscillates once every 3 seconds, or a period is 3. It's going to start when it's compressed by 5. It's going to be up here at 5, and we're going to let it go, and it's going to come down, and so on. So what are we going to do with this? Well, first off, our period is 3, so I think we can find our B. So our period 3 equals 2 pi over B. So B equals 2 pi over 3. Okay, 2/3 of pi. Okay, let's see here. What else are we going to use? Do we want to use our cosine function like before? I think we do. Okay, but how about that exponential decay function that goes in front? Okay. So if this is going to measure the distance, okay, its position, distance from the ceiling, I think, again, we want to, hold on here. All right, let's just go to this 30 seconds per second. Notice on this one, here's our amplitude. Okay, it's just an exponential decay function. So if I write an amplitude function, I know we have to have our initial amplitude times e to the kt. Now, what's our initial amplitude going to be? Well, it needs to be 5, right? It's starting 5 units away from equilibrium, but it's actually 5 units less. So we're going to make that to be -5. There we go. All right, now what is that constant k? Well, we know that it needs to be at a decrease by 30% every second. And that's where it gets a little bit tricky here to solve for the k. We know t is going to be 1. Okay, but what is the amplitude then at 1 second? It has to decrease by 30%. So what I would have to ask myself here is, okay, if I decrease 5 by 30%, okay, that's 70% of 5. What number is that? So if I take 70% of 5, it's going to be at 3.5. So this would be at a -3.5. Now, thinking back to when we did our exponential and logarithmic work, let's solve this for k. We're going to divide by -5 on both sides. Let's see here. What's -3.5 divided by -5? Oh, it's 0.7. Why is that not a surprise? Because it's decreased by 30%. It's 70% of what we wanted. In fact, when you solve this equation, you could have just picked 1 here and a 0.7 there, and you would have been just fine. But I wanted to kind of talk you through that process of, I think it makes a little more sense to say, okay, if we're starting 5 away and now we've lost 30%, where are we now? So we've got a 0.7 e to the k. So how do we solve for k? We take the natural log of both sides. That's k. So our amplitude function is going to be -5 e to the natural log of 0.7 t. Now, we said we're going to use cosine. We've already multiplied the negative to consider the fact that it's starting below here. So let's see, what do we want to call this function? let's just call it d of t like our last one. It's going to be the amplitude, like that. And then we're going to multiply by the cosine function, and our b was 2 pi over 3 t. Now, where's our midline? Our midline has to be 10, right? We push it up here, it's going to be 5. We're going to let go, it's going to go all the way down to 15 below, and then it's going to come back up, and it's going to be just underneath 5 away from the ceiling, and then it's going to come down, it's going to be just above 15 below the ceiling, and so on. Let's take a look at that function. All right, let's put a -5 there. And then this was what? The natural log of 0.7. Now, remember on the last one, we also had to move this up. So let's add 10 to that. All right, let's do the same thing here, but then I'm going to get rid of the negative to bound it on the top. And now what I'll do is I will put the -5 e to the natural log 0.7 times t cosine of, what did we have here? We had 2 pi over 3, and then we're going to move it up 10. All right, so does this look the way that we wanted it to look? Well, at 0 seconds, it needs to be 5 units away from the ceiling. That looks good. Then it needs to gain in its distance away from the ceiling. Okay, come back down to go to 15. However, because it's damped oscillation, it can't get all the way to 15. Okay, it's going to start damping right away. So we can see there, we only make it to about 12.97 inches below the ceiling. Then we come back up. Now, what was our period on this? Our period was 3 seconds. We can see it doesn't end up perfect, okay, but it gets pretty close to get that period to be about 3 seconds. It ends up being a little bit short here when we do our multiplication, and that's okay. But we've come up with a nice model. Okay, so let's just kind of review some concepts here. Figure out its period, use that to solve for b. Write a function for its amplitude. If it is really damped, that would be an exponential decay function. Think about your initial value, whatever information they give. You can plug in as a point, solve for k. We should all be really comfortable with that. And then put them together. Okay, remember to consider your midline, your equilibrium point as well. All right, thanks for watching.